Welcome everybody. This is another HIT seminar. This time we have Sebastian Scheid, and he is coming to us from CERN, actually, being on a working vacation, but in the area, and it was very nice to grab you here. Sebastian will be here with us also tomorrow, so if you want to talk to him one-on-one, please do so. We're planning for a pizza today at Jupiter. You have seen the message. It would be good to let me know the head count. We want to be there at 6. I have more or less the head count, but it would be good to know. So Sebastian graduated in Frankfurt. He did his PhD there on dielectron production and proton-lead collisions, and to see how the cold nuclear matter effects look in those collisions. Following earlier work on heavy flavor. So very extensive knowledge on the electron production, but he also was driving the dielectron studies for the ALICE 3, and he was one of the key people writing actually the proposal in this area. And currently he's a research fellow at CERN, and he's working on dielectrons in the new collisions that we just recorded. You have seen the hit by Ant 2 weeks ago, or some time ago, of the oxygen-oxygen collisions, and he's also working on the new vertex detector for ALICE 3, and he's also coordinating a physics analysis group within ALICE. It's the core where physics is created on topics. For all of those who are in ALICE, he's working on low-mass dielectron. So Sebastian, thank you once more for being here.
Thank you very much. Thank you for the introduction. Yes, and yes, as already introduced, my field of work is the dielectrons, and this seminar will be about the present and the future of dielectron measurements with ALICE. So I will start from the beginning. So, I mean, if we're looking at ALICE and heavy ion collisions, which the experiment is made for, one thing that we're after is to map out essentially the QCD phase diagram, right? And I brought a sketch here, like, about the understanding that we have of it. So if we draw it as a function of the barochemical potential and its temperature, we know that there is somewhere a crossover phase transition between the hadronic matter and quark-gluon plasma and the first order phase transition, and then we should have a critical point. Now, if we think about matter, how it exists around us, we're somewhere here. But when we look at how it was in the early universe, it probably started somewhere here and then cooled down and arrived in the hadronic state. Now, this is one way to draw this, and if we now do a bit more schematic in heavy ion collisions, we recreate this sort of little Big Bang in the laboratory. So we collide two heavy ions, they start interacting, they form the state of matter, like the quark-gluon plasma, which then cools down, starts producing hadrons, which are indicated here, but they're still interacting, and in the end, everything ceases to interact and flies into the detector. Now, this is what we, like these early stages are what we want to look at, and what we are doing is to do so with electromagnetic probes. And electromagnetic probes are quite nice because they are essentially produced in all these collisions, so they are quite early produced, and leave their production zone essentially with negligible medium interaction. So essentially, you produce a photon here or here, and it will escape. And now, just for the, let's say, nomenclature or the wording that I use, so when I talk about real photons, I really mean a photon that arrives in the detector. When I talk about dielectrons, I mean virtual photons, which then do this process of internal conversion into any plus or minus pair. And then we can look at different phases. So we have a pre-equilibrium phase, quark-gluon plasma phase, or hot hadronic matter, where all of them produce electromagnetic probes. And this now is actually the advantage of electromagnetic probes, because if we look at hadronic probes, they have a bit limited sensitivity to these early stages, because we measured this part here in the back, right? So if they're produced here, they still interact. For the quarks, it's similar, they still interact, and then, of course, you can still learn something from the interactions, but with the photons, we actually don't see these interactions, and this is the nice thing. All right. Now, for the real photons, being a bit more, let's say, qualitative, here as I just said, we have these different sources. So we have thermal sources, hadronic matter, or the QGP. And if we look at, for example, the energy as a function, or the yield as a function of the PT, we can also order them a bit. And this ordering goes somewhat with the time, right? So at the lower momenta, we have the hadronic phase because it's just not that hot anymore. So the phase space that we have is small, produces more low PT particles, and then essentially going up or going early in the collision, the spectra get harder, and this kind of populates different momentum ranges. Now, the problem if we look at real photons is that we have a blue shift. So in principle, we have this source, and I explained this before, it expands. So if I radiate a photon from this expanding source, it gets blue shifted, and if we would now want to look at the temperature, which is proportional to the slope of the spectrum, it's blue shifted. So the effective temperature we see is higher than the temperature of the medium that it actually is produced the photons.
That's still a question. How you get the pre-equilibrium?
Well, I mean, what do you mean with how do you get it?
Why it goes back?
Why it's so hard?
No, why it's actually turns out goes zero.
Okay, this is mainly because I sketched it like this, so we don't really know. So we don't have, this is more, I think normally if you look at the models, they look somewhat like this, but this can also be that there is.
No model give you that. So you have huge uncertainty there.
Yeah, exactly. So the uncertainty is, we simply don't know. This is, I think, the main.
So that could actually overshoot your hadronic matter or QTP.
I think there is, well, I think the uncertainties are so large that that I wouldn't be able to say. I think that the calculations that we have would say no, but there are some. Huh?
Which calculation?
There is a paper by Schlichting and et al. Where they do this, but there the main uncertainty is really the scales.
Okay. So what is a very soft photon emitted in free equilibrium? And hard photons you can just attribute to atomic processes. Soft photons is some kind of Bremsstrahlung process, or what do you have in mind?
No, I don't have anything in there. So if you do probability calculation, it's erroneous.
That's a perturbative calculation.
Yeah. So that means you don't know. You don't know the answer.
I think actually so there are also calculations by this group of CERN, Schlichting, and I think Oscar Garcia is involved. They have somehow this what they call the pre-equilibrium phase. So let's say a not equilibrated system, but they cannot really distinguish if this is a thermal or pre-equilibrium, right? Because the processes are the same.
Wouldn't a useful definition be soft photon production and product collisions? That would be, by your definition, perhaps free equilibrium. Does that actually diverge? Does the measurement diverge? I mean, people must have measured that.
We did not measure it at LHC, but I think there are measurements that, well, I mean, the problem is mainly the hadronic decays then. Yeah.
Phoenix.
I'm not so sure.
Well, that's how they get their
They use a dielectron.
Use what?
They use a dielectron.
That's right.
But if they see a divergence, I think there are measurements of soft photons then from, I think.
Right, not soft real photons. Soft real photons are possible.
Okay.
That's right. That's using.
Okay. I just want to remind everyone there's a huge uncertainty.
No, the uncertainty is. Yeah.
I'm not really familiar with the photon production, but could you give me like some brief overview, like what kind, when you say the photon production from the pre-equilibrium, like what kind of mechanism?
Anything that shines.
Anything.
I mean, anything that, as we said, it's really anything that is produced by the system, so you can have quark-gluon Compton scattering in a way, right? But not in an equilibrated system. So you don't have a thermal system at this point.
Okay.
Move on. And I mean, as I said, right, so the dielectrons, essentially, it's the same sources and so on. The main difference now is that we're not looking at the momentum of the photon, but at the mass of the virtual photon, which is unaffected by the blue shift. This is the one thing. And then what you see is what I tried to sketch here is that there's actually some structure in the hadronic matter part, which is mainly because the processes in the hadronic matter, one can imagine something like this, that you have pions essentially scattering off each other, forming a row. So this is a vector meson, which couples to a virtual photon and then decay. So you're left with some structure of this. And by this, you become sensitive to the indium spectral function, which is then connected to the restoration of chiral symmetry, which is, yeah. We'll not go so much into detail for this, but just so you heard it. Okay. Now, I essentially introduced all these sources and essentially showed you that by looking at different momenta or masses, we hope that we can somehow disentangle them. However, the problem is, as I already mentioned, that we have late-stage hadron decays, and they, of course, more or less produce a lot of photons and electrons and positrons, which we then have to somehow subtract. And we do this by this so-called hadronic cocktail, and you will see several hadronic cocktail calculations later, so I wanted to just give an introduction what we mean by this. And in principle, this is the best possible estimate of the contributions to the spectrum from hadronic decays. We try to base them on independent measurements. So for example, for the, let's say, this pi0 part, that we take the measurement of the pions, then we put them through a Monte Carlo that includes the detector effects and everything, and see, and let them decay into plus and minus pairs and see what comes out, right? And this we do for the pions, for all the vector mesons, the JSI you can see, and then you can see this broad structure here, which comes from the charm, which is the heavy flavor. And this is actually for most of the measurements at LHC the most challenging part because the cross section is just so high. And on top, these sources are modified themselves. For the pions, for the omegas, pi's, JSI's, we can measure them actually in the same systems. So these effects are already included. However, for the charm, it becomes more complicated because cold nuclear matter effects and energy loss play a role. And this is an additional complication for the dielectrons because in the photons, they are simply not a background. Okay. And now just some more on the wording. So I will use low mass region essentially for everything that's below the phi and mainly dominated by the hadronic contribution, and then the intermediate mass or IMR between the phi and the J psi, where we expect to be sensitive mostly to the thermal radiation. All right, and with this I want to give a short, quick summary what I was talking about so far. So electromagnetic probes are produced in all stages and carry the information undisturbed to the detector. Momentum and mass should allow us to select the different sources of the electromagnetic radiation. And by this, the production time in the collision, and then for the dielectrons versus photons. So in principle, the additional invariant mass information gives us a tool to circumvent the blue shift, which we then don't see. However, we have a smaller statistical precision because we have an extra electromagnetic vertex in there, and additional backgrounds as I just discussed. And from now on, I will not talk about the photons anymore, but focus on the dielectron measurements that we have. Okay. Good. So just for everyone who's not familiar with Alice, so this is a sketch of the detector itself. And when we talk about dielectrons, we measure them in the central barrel. We use mainly 4 detectors for this in a tracking system for vertexing, tracking, and particle identification. We have a V0, 2 V0 scintillators in forward and backward rapidity for the centrality estimation, the time projection chamber for particle identification and tracking, which is this large blue cylinder here, and then the time of flight detector is the most outer detector we use, that we also use for particle identification. Okay. And then I want to come to the first result. So this is the result of proton-proton collisions at 5.02 TeV. Exactly, and the strategy here is essentially that we measure the dielectron production in pp, plet, and let at the same collision energy to estimate from pp the baseline, also for the heavy flavor production, and from plet to identify possible modifications from cold nuclear matter. And then, as you see here on the plot, this is now the data in these blue points compared to the hadronic cocktail calculations, as I explained them before, and it's actually quite well described I just want to add here that the uncertainties here are quite small, and that we described it in the intermediate mass very well, because there we use the fit. Essentially, we fit the charm and beauty distributions here to then extract the cross-section of the heavy flavor, which we then can use, because in principle you could also do it, and this was done before, just from taking the measured heavy flavor cross-section, but then you get all the different components in, like the fragmentation fractions, the fragmentation functions, the uncertainties on the cross-section itself, the branching ratios, and so on. And if you measure it just in this decay directly, you have all of this in, assuming that going to QLED or LED, this doesn't
Sorry,
change.
say that again. The heavy flavor cross sections are free parameters in the fit.
Exactly.
So essentially, they're being fit by the intermediate mass region. So that's where
The fit is actually constrained to the intermediate mass.
Well, but I'm missing something. I mean, that's what I wanted to ask. I don't remember, because you need to know something about the ratio of charm.
That's exactly what I was getting at. That's right.
So
So
it's gotta be some.
the purple and the purple and
Now you were
red.
telling us that that's not the case.
Very
No. Okay. So because this is shown only in 1D, we do the fit in 2D. So we do it in mass and PT, and the high PT part is sensitive more to the beauty.
So
we don't fix the ratio between them.
because the purple and the red, I guess it's red, the charm and the beauty, they're very similar in shape. You can't.
Yeah. No, you have to do it in 2D.
But maybe not a fix the ratio, but you need to know something, because if you let them free completely in your fit, you can have unphysical charm to beauty. You can get unphysical charm to beauty ratio.
But we get a physical one, so this we can tell you.
So you check it
No, but
against
something
charm
has to-
calculations.
Yes.
Yeah. So what we
There has to
did.
be some
So
constraint.
what we did here is that we used
Controls,
two different generators. So here you see this is ProHack essentially that is coupled to Pythia shower to essentially get the mass and PT shape.
But the
So
total charm cross section
and then we extrapolated back, and then we compared it to the hadronic measurements, and then within the uncertainties were actually there.
Ah,
So
okay.
it works.
So the total charm and total beauty comes in some way.
Well, we put it as a control, so to say. But what we see is that we actually have quite a sensitivity on the generator, actually. So depending on the generator, it changes because they have different rapidity distributions of the quarks. And then for this publication, I mean, in the end, the chi-square is more or less the same, so they describe it very well. And I think the number of points that we fit is something like 130, so it's not only these five. It's only more than 2D.
Run two, of course.
This is run 2, yeah.
So I have a question about what you're not showing. Keep on going and let me.
Shin,
Shin, go ahead.
you have a question?
Yeah, I'll come back my questions. Go ahead, Shin.
Yeah, thank you. Can you hear me?
Yes, we can.
Yeah.
Go ahead.
Yeah. Since we are interrupted, I just want to ask a question, maybe two questions here, Sebastian. First is this data point at roughly 0.4 GeV. I look at the ratio.
Shin, can you speak slower? I think there's something with voice quality.
I'm sorry. Yeah. So I'm looking at the data points around 0.35 to 0.4 GeV. It looks like there's a kink here.
You mean
here?
here?
Right. Looking at the ratio, it's not a small deviation.
Yeah.
This is also the reason that when we talk about the romance and broadening this kind of application. The question is actually in the cocktail simulation, did you fold in the mass resolution in your calculations, or this is purely generated? Okay.
No. So in the cocktail we put the momentum resolution of the single tracks.
Okay.
So this is for the electrons. Okay. This is folded in, and then yes, as you say. So this is it goes up and then it looks like this continuity.
Yeah, it looks like then potentially in the data there might be a little broader, because look at the pi0 peak region. There's a systematic. The ratio also is systematically rising. So the data is a little bit broader on the which means it's not a nice, but that's I think. Certainly, if you consider uncertainties, now good, but when you're pushing for precision, then it's
I totally agree.
Yeah. Second question is that on top of the bottom, I'm a little puzzled about the BB bar, the line shape of the BB bar, it dies out at high mass. Is that because statistics, or it's the real shape was just goes down as CGV above?
Yeah, so that the beauty goes down is actually an effect of the sign of the pairs, because when you produce a B and a B bar quark, right? So quark anti-quark, what you have is either you have both going into a B meson directly, and then both B mesons decay, and then you get an E plus E minus pair. But what you can also have is that one of the B's decays first into a D meson, and then the D decays into the lepton. And this always gives you essentially a pair of a like sign pair. So this always gives you a minus minus or plus plus pair.
Okay.
And if you play this through and then you subtract the one from the other, because this is what we do in data, right? We subtract unlike sign, the like sign from the unlike sign. This actually gives you this shape, this kind of, because otherwise all of them are smooth, but they have different mass shapes.
Okay.
Yeah.
Okay, thank you.
Ask another question?
Yeah.
So, right, so I'm asking about why you stop at 3.5. So in fact, it's not that steep a spectrum. It's fairly flat.
Yeah.
And your last error bar is not terrible. And I can imagine there may be significant data out to 4.5, and that's where charm is probably completely dominant. So why did you stop at 3.5? Why didn't you go?
Statistical error.
I understand that, but I'm saying it's not yet, it grows, but it's not crashing like a jet spectrum. It's fairly flat. So why don't you go to 4.5 and constrain the charm better? What's the issue?
Well, in this case, actually, it's the statistics and then the Monte Carlo on top. At some point, you have to, and we tried it essentially. So if you look at the papers, you will find some where we go higher to 4 GeV, but then it's mostly like, okay, do you still find a point?
I see, so that actually the spectrum crashes above the size.
Well, the statistical precision of the last point is actually low.
I mean, you could put one more point essentially, but then you would have one more point which has a small statistical precision. Okay. But for run 3, this is what we do. So we go
run three, you have,
exactly.
That's actually what I was asking about run 3. Run 3, yeah, much more dynamic.
I will show the spectrum. So, yeah.
Okay, sorry. Why PowerEC? What is so special about PowerEC, and why not FONLL or whatever else there is?
So because PowerEC you can couple to Pythia.
Okay.
Right, because you need a shower
So
somehow to
FONLL,
produce
you can also couple just by decaying the CC bar.
Exactly.
The charm cross section.
Exactly, it gives you a cross section, but
there are differences, right, between PowerEC and FONLL. FONLL always tends to be, I think, higher.
I don't recall. So in principle, we never used the full cross sections from Pythia or PowerEC.
Mm-hmm.
So we only needed the shape somehow from the event generator part to then would go back to the calculating the cross section from the charm section.
Yeah. Sorry, technical. Yeah. Yes, please.
Are you done?
Yeah, go on.
So it seems like you have a lower PD cut for electron, but you don't have that for dielectron. Did you do acceptance correction?
No. There's no acceptance correction. So essentially, we project over the acceptance hole. So if you would look at it in 2D, you would see the hole. So the full acceptance is only about, well, it's not even full acceptance, but below 400, they essentially would see a circle if you look at it in 2 dimensions. Which is also what we do then in the cocktail calculations.
So that means you don't have very low PD contribution.
No. Well, we have it at, we have it at higher masses. We don't have low PT, low mass. We have some actually, so I don't have the data here, but we have one special runs where we reduce the magnetic field, and then we can go actually lower. So then we can go down to 80 MeV instead of 200. Okay. All right. So, but in principle, what we learned from this is that we have the baseline actually quite well under control with this. And then I want to come to the proton lab. So essentially, the strategy here is more or less the same. It's again, the data is measured. We compare it to the cocktail, and the light flavor cocktail here is based on measurements in PLED, while the heavy flavor cocktail is based on the proton-proton measurement of the cross-section. And then we scale it up with the number of binary collisions in this case. And this then gives you the red and the magenta.
So these are, in this case, the heavy flavor is not free.
No, it's not free. It's not free. So because what we wanted to check is essentially if we would see some sort of modification due to post-nuclear matter effects, and since we didn't see anything, we also didn't do the fit.
This is like obtained from Glauber model. It's consistent with the what you.
Yes. So the end call is from Glauber.
It's just A. I mean, if you have an efficient minimum bias trigger, it's just scaling by A.
Yeah. No, actually, it's scaled by A. Then, but you need to then get the nuclear overlap.
But you also LHC invariant, they have cold nuclear effect, right?
Yeah.
Yes.
I was going to say, what do you expect from shadowing?
Well, I think from so it's a bit. We have measurements in the D mesons from Alice, and then the effects are something like 10%. But within uncertainties, then of this, I mean,
You wouldn't be sensitive.
Exactly. So this is what we see. But the problem is a bit what we didn't know in the beginning is like really what is the kinematics of the thing. So essentially the dielectron pair that comes from charm, right? You have two charm quarks, they hadronize into D mesons, these decay. So what is actually the D mesons that you have and how are these PTs correlated? And I think we're somewhere like the mean PT of the D mesons is like 2 to 4 GeV, which is also where you don't expect many effects.
So the CLM is complex.
Yeah. So essentially, I mean, in the paper we did an estimate what we would expect from EPS09, which more or less describes what we see in the D meson measurements, and then you expect a 10-15% effect. Yeah. But yeah, since the data was even above the expectation.
Power times A, right there.
Yeah.
Right. No.
Exactly. Yes. So in principle, from this, I mean, this was the same paper. So what we concluded is that we had, let's say, the baseline quite well under control, and that if they are present, the quote-unquote matter effects are small. Okay, and with this, I want to come to the LED measurement. So that now the plot gets a bit more complicated.
Sorry, back to PA.
Yes.
Did you ever look at the change in distributions if you select an event activity?
No.
You're asking for trouble, Peter.
No. We actually. So we had an analysis. We actually had an analysis that was not event activity directly. It was more. It was a centrality analysis, but it never concluded really. Unfortunately.
Oh, why?
Because the person doing it had to hand in the thesis. And yeah, it was. There were some technical issues with the calibration and so on, and then we never managed to put it into a paper.
Yeah.
But there was also nothing like in particular seen.
So is Gaussian contribution constitute some?
No.
No.
It's actually something that we're discussing again now.
It's
So-
buried way in the tails, right?
So we, in the first publication, because this is now run 2 data, we had a publication in PP70 where this actually came up because nobody really knew, and we did some estimates based on Pythia. And then we realized that at least in the intermediate mass, where we would maybe could expect something, the contribution should be below 1%. But now actually, so with run 3 data, we want to like revisit this. And
Isn't it overwhelmed by charm everywhere at the LHC? Pretty much.
That's the point, right? So it's below 1% because the charm cross section is so high. But then maybe if you go out to higher masses, you might get a handle with high precision. You might be able to put an upper limit. This is what we're thinking now.
Hard game.
Okay. Then I want to come to LED. So yeah, with LED, the plot gets a bit more complicated, and the main thing is that what we now did is that we again took the light flavor measurements as before, but for the heavy flavor now we have 2 approaches. So one is that we simply did what we did in PLED, which is that we scaled it with the number of binary collisions. And I will now only point to the ratios, right? And this is essentially what you see here. And then what we also did is that
So this is what's centrality, sorry,
0 to 10%, sorry. Yeah. So this is very central LED. So this is where you would expect the biggest effects of energy loss, but also of thermal radiation. And exactly, so we did one cocktail where we just scaled it up by the number of binary collisions, and then one where we included the initial and final state effects, which were based on measurements of the heavy flavor, electron RAA essentially, and we used EPS on 90 and PDA because we have to disentangle them a bit. And I first want to focus actually not on the intermediate mass, but on this lower mass part here. Because as I explained before, this is essentially also where we would expect some thermal radiation from the hadronic medium that we form. And then you can also see that we're not so super sensitive here, right? So I mean, if you change these cocktails, the data points don't really change that much. And we see this kind of hint.
Sorry, that went too quick. The blue and the two.
So upper and lower is the two different cocktails, which treat just the heavy flavor part differently. Yes.
The blue is N-call and the other is RA.
And I mean, it's a bit obstructive, right? Because the N-call has quite small uncertainties, but we're quite sure that it's wrong. Because we know that there are effects, and there are sizable effects. And then including them in the second part, you see that the uncertainties start blowing up, essentially. Yeah. Yeah, and as I said, we also see that there might be a hint for something extra here in this lower mass region. So essentially what we did was the first thing that we compared it to model calculations. So in this case, okay, now because we have two different cocktails and then we have two different calculations, that's why we have 4 curves. In principle, the models, this many-body theory approach by Ralph Rapp, which essentially calculates the rate of photons and then transport code PHSD. And I mean, if you look at the curves, I'm not sure how well you see it, but they are more or less on top of each other. So at least in terms of what they predict, they are not that different. Exactly, and at least up to, let's say, 500 MeV, this follows very well the curve that we see, or the data that we see, and then it breaks down.
Shin already, I want to ask about that point. Shin already asked, let me ask again.
Yeah.
Here it's really dramatic, and we're going from 500 to 550. So you must have done all kinds of exercises, different binning.
Yeah.
You know,
and we really don't
put
get it.
Put it under the microscope. So you're showing it. You must be convinced it's physical. So what's the reason for this?
So I think so because I was looking at it again. I will maybe just go to my backup slide that I put on this. No, still, sorry. So in principle, so we did all of these checks. We rebinned, we tried a lot of things. However, we didn't manage to somehow see change.
Reshare.
Yes. So, in principle, okay. So now what you see here is essentially on the right hand side or your left, the raw spectra, right? And this is now in red, the same sign distribution. So what we do is we take the same sign, we subtract the background, which is the unlike sign, times a correction factor for the acceptance. And then what you essentially, and then in blue you see the raw signal essentially. And what you see is that it already breaks down in the raw signal. However, this is also the area where our signal to background is really the worst. So at the moment, what we believe is it's really a fluctuation in the background somewhere, which then just dramatically blows up. So this was also tested like several times, and this is also why the publication.
You divided data sets, tried different.
Yeah. So we really couldn't figure it out. And then at some point we run out of statistics to do it more differential, to be honest. So.
Just to be clear, when you say you think it's a fluctuation, does this mean that you think it's fluctuating up, like it's fluctuating down at 550, or it's fluctuated up at 500? Or below?
Well, so what we think is that actually the background, so okay, what we think is that it's actually the background fluctuating up. Or the signal down, right? But the thing is that because your signal to background is, we're here somewhere between 10 to the -4 to 10 to the -3, right? So like very small changes in this, or yeah, but it's also in the it's in the raw signal. It's not somehow the efficiency or how we treat the whole thing in the end. So, but then we actually ran out of statistics to do it more differential. If you go to more peripheral, it actually looks much better, but then your signal to background gets much better. And we are now, well, this is definitely something that we are trying to investigate now with the new lab data. It has different issues, but yeah.
So this is run 2, and now in run
This is the run 2 2018 data.
in run 3 we have order of magnitude more, or
Yeah.
2 orders of magnitude. I don't know.
One order more. At least in central, because this was central triggered, right? So we don't have that much more data. But one order of magnitude more, and then also
And a much more uniform ITS, which must play into this. I mean, that must really complicate the background estimations. There's a
exactly
ITS non-uniformity.
Problematic sector A, whatever.
the ITS, but then also so what we this is so there's
I think both would be better than 3.
So also what we also see is that it's the PID with the top at some point. So what's labeled here as the background is essentially the like sign times this acceptance correction factor, which we estimate from mixed events, which has a lot of statistics, but then, I mean, if you do it wrong on the per mil level, it gives you large fluctuations. So this is what we're putting a lot of work in now. Yes.
In Phoenix, when we did this measurement, we also looked at this bump in the low mass region.
Yeah.
But later on, we identified that it was because of the misidentified pions. Because you are looking in the low mass region, where your high PT contribution is more. And in Phoenix, at high PT, the identification between pions and electrons was not that good because it was coming from rich. And in the gold-gold collisions, when we made our cuts harsher for removing that misidentification problem, this bump seemed to flatten out a lot.
So with a harder pion cuts.
Yeah, exactly. With a lot harder, better electron identification. So not to sound anticlimactic, but whatever I saw from over there, I'm just passing it out.
Yeah. No, it's good. So what we saw is that actually what is actually also something is the kaons, because if you have a phi to kk, and you misidentify those, you actually get a bump in this region. But this we also checked. So
we saw that electrons and the pions which were in the secondary.
Sorry guys, I don't want to Shin, you want to ask your question, and then maybe we should get back to your slides. Shin?
I probably take off because I have a similar questions to previous people commented about the purity of the electron sample.
Okay, so maybe we can come back to it later.
Yeah.
Yeah.
All right.
Maybe you can come
Sorry.
to your
All right. So I will just go back to my original slide.
Better hurry up. He probably has a flight to catch in a couple of days.
Couple of days, yes.
So all right. So yes. Share again.
Well, we have a pizza booking at 6 p.m. So that's it.
Finish by 5:45.
That's it.
All right.
That's a sign of a good seminar if you can't make any progress with your slides.
Yes, that's right.
So exactly. So in principle, what we see is that without except this part where the data really looks weird because it's also this jump, right? So it looks unphysical. We see essentially a contribution that the models would also tell us there is, and I think one of the questions now, okay, what does this mean for the photon production itself? So what we did is we followed the method that was, I think it was actually developed by Phoenix, which is the extraction of the direct photon fraction, small r. And this is essentially that we say, okay, we have 3 different contributions. We have a heavy flavor contribution, we have a light flavor contribution, and we have a direct photon contribution. For the first 2, we have the cocktails that give us the shape as a function of mass, and then we use this Kolvada equation, which connects the real and the virtual photon production. This is valid for masses that are smaller than the PT. So now we're looking at masses at some 100 MeV and PTs larger 1 GeV, and essentially perform a template fit. And this we do in different PT intervals, and reconstruct essentially this, or extract this small r from this, right? So now you see essentially the fraction of direct to inclusive photons, which should be then the fraction of the photons that we're interested in to all the photons that come from the decays. And then if you use this and the measurements that we have from the neutron mesons and the inclusive photon spectrum, you can translate it to a direct photon spectrum, which you see here. So this is now the invariant yield of the direct photons compared to model calculation, which is now real photons. So this is by Charles Gale and collaborators. And this now also includes essentially all the different phases. So there you see essentially a prompt, the pre-equilibrium, and the thermal phase, which is QGP plus hadronic. And then we see a ratio, and then essentially, at least in this PT interval, what we see is that the model is kind of on the upper edge, but within the large uncertainties that we have. So at least there we don't see something like it's seen at RIC, where these models tend to not describe the yields if they describe the flows.
Dominant uncertainty is
exactly.
What is dominant? What is the largest uncertainty?
I think the largest uncertainty here is actually the eta to pi-n ratio that goes in, because if you put the eta to pi-n ratio, this would change your light flavor curve, right? So this changes where this shoulder starts, essentially here. And then this directly changes a bit. And at low PT, we have very little, well, we don't really know the eta pi ratio that well, which is one of the main problems.
So for run 3, I don't know where you're going, but if I go back to your, the next slide.
Yeah.
So we're definitely going to shrink the statistical uncertainties.
Yes.
Are we going to do something about systematic uncertainties?
We really hope so. But it's really like these measurements of the neutron mesons are essential there. And these are normally performed in the calorimeters.
One can use the conversion techniques.
Or the conversions, and with the conversions we struggle a lot at the moment in terms of the...
Calorimeter is not good at all.
No.
I would use the conversion and run 3 with the uniform light. It must all be messed with that. It must work a lot better.
It should work better in terms of also the...
And with these conversion techniques, you can go down to 1 GeV, I think.
I think the main issue there at the moment
less
is the
material now, though.
Let's have more data.
I think the main problem there is really the tracking and associating the tracks to the right collisions at the higher rates.
Oh, we have a continuous readout problem, right?
That would be solved.
Exactly. I think it's a solve. So it's on the way. A lot of smart people are working on this. Exactly. All right.
Very good.
And then I want to come back just really quick to the intermediate mass, right? And I mean, okay, as I explained, we now have these two different cocktails, and essentially what you see is if you include the final state or the interaction with the medium and the nuclear matter effects, essentially the central value of your cocktail moves closer to the data, right? So they are more or less on this black line, which is the one. However, the uncertainties just blow up. And this is really something where I don't think that we will get much better if we continue like this, and essentially have to essentially put all these different, let's say, tricks into the cocktail to include it. So we need to find a way to handle the heavy flavor contributions.
No, but coming back to the point I said before, run 3, you can go above the J side. You don't have your. So what are the dot dashed lines in the upper?
The dot dashed lines in the upper are the different cocktail calculations. So this is like essentially. So here, this is the model calculation.
So can't you constrain charm if you go above the J side?
You could, yes. The problem is then you're in a different PT region again, right? So you're not sure how this then looks at the lower masses. So the cross section, yes, but the modifications are PT dependent.
But in the high masses, your trillion contribution will also start to grow, right? And that is something you don't know at all.
Really? And Trillion was maybe I got it wrong. I think Trillion is tiny.
I think there are measurements by CMS which start at 20 GeV. And this is as low as we know the trillion.
I mean, I agree with you. It can be constrained pretty well in the high mass region, but then the other sources are also becoming uncertain.
Yeah.
The trillion and other things.
But what we want to do is actually to use the distance of closest approach, which should also give us a handle on the Brilliant actually, which is essentially just using that we have finite decay length of the charm and beauty hadrons. And then we constructed it this way that we essentially say, okay, we have one track, we extrapolate it to the primary vertex, and then we take the distance of closest approach from this, and we normalize these to the respective resolution and build a pair variable with this. More or less the definition of this. And we did this already in run 1. So this is the analysis of run 1 PP 7TV. And now we're looking in a mass region, which I will not show again ever. But this is essentially above the pi up to the phi. And here we have a mixture of just both. So we have the resonances, we have the eta mainly, and the omega and the phi. But we also have charm and beauty. And this is now not done with a fit. So this is essentially taking DCA templates from Monte Carlo, taking the cross sections that we know in a way, and then putting all of these essentially as a cocktail. And then you can see that we actually managed to differentiate between these different sources here. So this was exactly, so this was the run 1 result that we did here, just to check if it actually works with the tracker that we had at the time. And this was then extended actually to the LED. And now you see the intermediate mass region. So this is now, again, where we are dominated by charm and beauty, and expect some sort of thermal radiation from the QGP. And now it's again that essentially, so what was done here is now really that the fit was performed. So we put these templates from Monte Carlo, but we performed the fit. And in the legend, you can see it a bit. So this is essentially using charm and beauty with an cold scale cocktail. But then the fits essentially suggest the scaling of these. And these scalings are what we kind of expect from cold nuclear metal effects. From, not cold nuclear metal, simply from the expectations from the electron array, heavy flavor electron array. And what the fit also tells us is that it prefers an additional thermal contribution. However, if you the statistical precision on this is really limited at the moment. But this way we can turn it around essentially. So now we're actually statistics limited, if not systematics. Yeah, and that's on this. And with this, I want to move to Alice in run 3. So as it was discussed already, we have a new TPC, so the continuous readout. We have a new ITS, which gives us less material and a better resolution, which then improves these DCA studies a lot. And to complement of this, we have the O² online reconstruction. And this is now the dielectron spectrum in PP, 13.6 TeV from run 3. And here we can, okay, I did not show the plot, but we can actually go out to 12 GeV. So, and then I think the statistical uncertainty starts showing up there. What we also see again is that we have this small bump here, right? And this is again in this mass region where we saw it before. So this is really something that we're looking into right now, but now we have the statistics to do it with differential. I think we estimated it's at the moment, like taking all the uncertainties into account at 1.4 sigma that we are weighing. So trying to understand it, but overall, I think this is already a good agreement with the data within the uncertainties that we have and hope to reduce.
Is that thermal production?
Huh?
Thermal production.
I would not be that that bold to claim thermal production from this at the moment, because in principle, I mean, if we would see something like 50%, 50-60% thermal production in minimum bias PP, I wonder why nobody else saw anything.
Maybe a bit high, right? Yes.
But I also don't know what models will. I mean, if you ask Ralph Rapp, he will give you a number for this. You could maybe just ask him and see. But at the moment, I think we really need to, in particular, check the eta to pi in ratios, which is going in there. But also, if we maybe have some effect because we had the acceptance hole, if we maybe have some resolution effects in the detector that we didn't fully understand yet.
Hey, we are not worried about the zigzag on the slope of the J psi.
This is actually pointing to a resolution effect. So what we think at the moment is that it's a resolution effect that shifts the mass of the J
It
side.
could be a misalignment.
Yeah.
It looks like a tiny.
I mean,
The
yeah.
cocktail has no freedom to.
I mean, in principle, the cocktail, if the Monte Carlo would be right, the cocktail would also map it, because the cocktail is essentially including the resolution. However, if we have a mismatch in the resolution between A and Monte Carlo,
Well, this is completely characteristic of a slight mismatch.
or misalignment of the ITS and the TTC.
Yeah, there must be something.
So
Something technical.
we have to look at it, because this was performed, I mean, with this APAS 4 of the 2023 data, where we probably don't get any reconstruction. So don't have it.
For what it's worth, in UPCs, we also have seen things like this. The peak is shifted.
Okay.
In some productions, not
In
all.
some productions.
Yes.
Okay. So maybe we should check
Okay,
some
let's
other
discuss
productions.
this at the Alice meeting tomorrow.
All right.
Move on with
I will
more
move on.
general.
So in principle, yes. So I just want to show this, which essentially shows the capabilities now in this region where we're dominated by heavy flavor, but want to look into it. And this is now again in this, like, this is now around the J psi mass, where we performed a fit again with BCA templates. You can see all the different contributions, charm, beauty, prompt, and non-prompt J psi, and they actually describe this quite well. And then if you perform this fit essentially in every single mass bin, you can start to essentially disentangle heavy flavor and prompt contributions, and this is what you see here in red. So in black, the spectrum from before, and in red, the heavy flavor part. And one thing that we were in the beginning puzzled by is this bump that we see here, which we then realize is just the V2J psi decays, because they have a high EC, and they show up at the J psi mass. Then we see essentially all the different peaks. But what we also see is that the best fit somehow claims some sort of prompt source in the intermediate mass, which at the moment looks quite high if we assume something like 1% from Brilliant, and which is something we're looking into right now, also with new data, with more data, to see if we can figure out what's going on there. But this is actually, so I think with this, we might be able to actually put at least a limit on the Brilliant production in the intermediate mass. And then going up to higher masses, I mean, you see it here, this is now up to 5 GeV. We don't see statistical uncertainty. So we should be able to really do a measurement like maybe between 5 and 10 GeV. So with this, I just want to mention run 3 lead. So we did the same essentially. And up to now, the data still looks a bit worse. Because, yeah, I mean, the signal to background is much worse, and also we're struggling a bit with the electron identification due to the high occupancies. But in principle, we see the same features. So this is now not a fit, but with cutting essentially on this, and we see again in this greenish here the peak structures, which come out quite nice, and then the very broad structure of the high DCA heavy flavor dominated part also showing the peak.
But why is it 10 to 90%?
Because we did not manage to extract a signal on 0 to 10. Which we have now, but there were a lot of, like, with new reconstruction passes, it looks much better. But this was
it's coming, but it should come.
Yeah. So with the new reconstruction, so this is what we had for quark matter.
I see.
And now we
Okay,
so at the let's say at conferences next year, you will see it also higher. All right. So yeah, this looks promising, but there's still a lot of work. And yeah, I will skip this summary, which essentially just says what I said before, and want to come to the future, which is ALICE 3. And the main feature is for dielectron analyses that ALICE 3 is planning to offer is this is a retractable tracker in the secondary vacuum, which should be the ultimate tool to do heavy flavor rejection, and then electron identification in terms of time of flight and rich with a large rapidity coverage. Just really quick, so we did some performance studies for this, where we used the cocktail, which was based essentially on what we had at hand. So essentially, we have the light flavor measurements in lead. We have heavy flavor, where we used what I showed before, including cold nuclear matter effects and with EPS 09. And then we have thermal radiation calculations of RAP. And then essentially what you see here is how you would, so this is essentially the thermal part, and how this would look if we just do it with essentially all detector effects included, but we don't do anything about it. However, if we look at the DCA of these, we see that they are actually quite different. And this shows now in blue the prompt contribution and then an evolution of the essentially templates of the DCA with our ITS generations. So it's essentially ITS1, ITS2, and then at least 3. And if you now simply cut on this essentially at a value of 1.2 sigma, which was a bit arbitrary, but because it was done in the study for ITS2, what we keep, or we reject 94% of the charm and 98% of the beauty, while keeping 27% of the prompt signal. And with ITS3, so what should be installed essentially in the next one shut down the charm that's left is like 17%, so something like factor 3 less charm than we would expect now. And with this, essentially the spectrum would look like this, and we would actually be, by simply cutting and not fitting or anything, be dominated by thermal radiation in the intermediate mass. Now what we did is to also subtract this cocktail. Now, because you cut it away first and then subtract it, we can see essentially small uncertainties. And what we now try to look into is essentially the spectral function and its uncertainties. So this is the axis essentially. And one of the questions was, would we be insensitive essentially to an effect of the chiral mixing of the rho and its chiral partner, the A1, where we expect if we have a maximum mixing an effect of something like 15%. And in principle, what we would need to differentiate is between the blue curve and the one here. And it looks like we should be sensitive to a shape modulation like this with at least 3. And should be able to do really precision measurement. Then what we did is to just go out in mass and see what the uncertainty on a fit of the temperature would be, and there we end up somewhere at 1.5 % of the statistical uncertainty, which is smaller by factor 2 to 3 from what we get from ITS3. However, we can reduce also the systematic uncertainties quite a bit because we can reject so much of the charm, which contributes here. And if the uncertainties are so small, what we try to do is to see if we can actually, with the large statistics that we have, do this more differential. And this is now essentially a projection of the temperature extraction in PT slices. And as I said before, if we now start at high PT and we go to low PT, we should also go back essentially or go through time here. And also there we should have a statistical uncertainty that's able to do this measurement, and then in this line you see also that we can nicely trace the temperature that comes from the model, of course, in this case, and that is probe the time evolution of the QGP. Now what we would need for this, yes?
You mentioned that temperature extraction is from the BT slices?
Yes.
But still fitting the mass, not the BT?
Yes, so it's essentially cutting in PT and then fitting the mass. And now I just want to mention some areas of the R&D that are relevant for this. And as I said, like one of the main points is the ridge, which would extend the PID of the detector to higher PT, the electron ID to higher PT. I put some numbers here. But the main point of the ridge is actually, so what the R&D focuses on right now is the choice of CPMs and their radiation tolerance and an additional electron ID. Where the main idea essentially is that so the ridge that is proposed has essentially a single layer aerogel radiator, an expansion gap, and then the photon detection. And with this, our PID would break down probably around 2 GeV, which means there is no pre-equilibrium studies, nothing essentially possible. So what's proposed right now is to actually put a gas in this gap, and then an electron would radiate in this gas where pi wouldn't, and there were some test beams now, and this now shows essentially 4 particles with a certain momentum, so 2, 3, 4 GeV. The mean number of clustered hits, so essentially how many hits does the detector find in the middle here. And then you see here on the bottom, you see all the pions, so they essentially make no signal, while the electrons, depending on the gas mixture here, so this is simple CO2 and then some mixture of C4F10. this actually works, right? And it more or less comes for free because we anyhow need a gas system for the CO2 to cool the detector. So this is R&D going on right now. The next thing is the vertex detector. So here, this is strongly relying on the ITS3 R&D when it comes to sensor design, stitching, the bending of the sensors. And then there's a lot of R&D or feasibility studies going on for this iris system, which is essentially this secondary vacuum detector that's moving. And there it's about the surface integration, the protection of the vacuum, the impact of the vacuum on the components, wires, bonding, glues, all of these things, because we have outgassing. And then because we move so close to the detector, about the mitigation of the radiation damage by cooling actually. And well, right, so this is the idea that the detector actually can open. And there I show here the test setup that we have for the test of the cooling, and there's actually a test beam starting next week on Wednesday, where we will put this into the SPS and see essentially if we cool it down to -30, if we can get a signal out of a highly irradiated chip. And with this, I come to my summary and conclusion. So I hope I could convince you that electromagnetic probes, and in particular electrons, are an excellent probe of the QGP. They are challenging measurements that benefit highly from the high rate taking capabilities and high precision tracking and vertexing that we now have with Run 3. And I think in Run 3 and 4 we're actually well equipped to carry out the first measurements of the observables, like the temperature. And ALICE 3 really has the potential to become the ideal dielectron experiment, and that is exploit the full potential of the LHC. Thank you.
Thank you very much. Okay, let me see. Shin, do you want to come back to your question?
Actually, I probably have a different question, but I think the PID that's been already discussed. I have a question regarding the new preliminary results in PP to show. Actually, it's this icon plot on the top. If we can go back to that slide.
Which one exactly?
The new PP preliminary results to show what matter. We talked about this kind of a
this one.
peak around 0.4 GeV. This is also the region that eta meson is in the cocktail eta meson dominance. How well is I know I need to measure eta meson. How well was the measurement, and how well, particularly in the low PT coverage? Have you looked into that?
So I'm not sure I got the question completely. You're asking about the eta to pi ratio there, or?
Basically the eta cocktail contribution. This orange line that's dominates the cocktail in this region, right? So that will affect the relation.
No, I think this is the main point where we have to look into now, because the problem is that, so there is a lot of data around, but the data is mainly from. So the constraint for this are actually from SPS still. So if you really want to constrain it to low PT, otherwise your fit is a bit floating at low PT, and this is what we want to look into, and possibly we can actually look into this with the. So Alice took data at a reduced magnetic field, where we should be able to extend the acceptance with measurements of the photon conversions for the eta at LHC energies, because this is one of the main problems we have now, that we don't really know the energy dependence of these ratios. But yes, so the eta is the main player here, and we have to understand it better. I think that's.
Yeah, thank you. Yeah, very nice result.
Burning question?
Just very quick. This large scale uncertainty, is this driven by the Vandermeer, or is there another analysis waiting for this?
Yeah. No, it's the 10% scaling.
Yeah, okay. Thanks.
Vandermeer scans, very important.
Indeed.
Thank you so much. So Sebastian is very kind. He'll be here with us tomorrow.
You come to the group meeting?